Hello and good morning, everyone. Thank you, Luke. This is about emissions. And after an introductory bit about what we mean when we talk about emissions and why they're important in global atmospheric chemistry, I'll be focusing on how emissions are implemented in global models, and of course with a focus on UKCA. The importance of emissions is based in particular on the fact that they stand at the beginning of the entire atmospheric chemistry chain. Emissions are the primary way how reacting chemical species enter the atmosphere. The other secondary way, obviously, is for them to be created through chemical processes within the atmosphere. But in order for this to happen, you need some reactant chemicals there. If you have an atmosphere that is entirely, that consists entirely out of molecular nitrogen, oxygen and argon, your options will be fairly limited. Without emissions, most reactive species would get oxidized, hydrocarbons would be turned eventually into carbon dioxide and water, and the atmosphere would cleanse itself. That would make the working lives for us atmospheric chemists much easier, probably, but the reality is that there is a constant stream of chemicals into the atmosphere where they then get chemically changed, transported around, and eventually removed. So this is shown to some extent in this cartoon, where emissions released at the surface of our planet enter the atmosphere, where then chemical chain reactions take place, where you have all these processes like photolysis, reactions, uptake on cloud, water droplets, interactions with aerosol, stratospheric ozone depletion. All this takes place. In short, everything about everything that we are professionally interested in as atmospheric chemists. Yes. So, however, the figure here can only show this in a very crude simplification, which is also true for atmospheric models. However, also in atmospheric models, emissions are very important because they stand here as well at the beginning of the entire chain, and you can have the most sophisticated model that you wish with a very elaborate, detailed chemistry scheme. You could put the entire master chemical mechanism into your model if you wish and run at glacial speed. If your inputs are not right, the fluxes that go into the atmosphere are not properly quantified, then you cannot expect the model to calculate results that match with what's happening in the real atmosphere. As the old saying goes, garbage in, garbage out. If your input numbers aren't right, then you cannot expect the model to provide you the correct answers for the right reasons. But sometimes you might get the right answers, but for the wrong reasons, which is a bit frustrating. Right. Yes. So I expect that everybody who works with a global atmospheric model eventually will have something to do with emissions. Even if you decide you do not want to change the source code, you don't want to touch the source code, you don't want to add to the chemistry, or do you want to change diagnostics that are in the model, if you want to take the model as it is, then you will most certainly still change the emissions. If you want to implement atmospheric chemistry, additional chemistry, then at the beginning of this process you need to think, you must think about where do my emissions come from and how do I implement them. So virtually everyone who works with atmospheric models will at some stage have to do with emissions. Okay, so about emissions, what types of emissions do we have? The most common top-level classification is the division between emissions of natural sources and anthropogenic sources. Natural sources or natural emissions are those that that occur as part of the biogeochemical cycles of our planet without human interference. So this cartoon here shows some of these processes. They might come, for instance, from the ocean as part of emissions of halogenated or sulfur compounds. They're often of biogenic origin, so you would have volatile organic compounds like isoprene or higher order hydrocarbons entering the atmosphere. Or another example would be emissions at altitude. Lightning is an efficient process that produces NOx throughout the troposphere. Right. Anthropogenic sources, on the other hand, are man-made processes, and what we consider as atmospheric pollution is largely covered by anthropogenic sources. Sometimes the boundary is blurred. You can't really say this particular process belongs to anthropogenic or natural sources. Biomass burning would be an example of this. So you have wildfires occurring naturally. However, you also have fires that are started by humans, for instance, in agricultural practice at the end of the harvest. In some parts of the world, it is common to torch your fields. So you could not distinguish there. Right. So natural emissions. Natural emissions, here are some examples of these. They often are dependent on other environmental factors, and this is part of the reason why quite frequently they're much harder to constrain and to quantify than anthropogenic emissions. Examples for this dependence is shown here in two slides. So here we have the temperature dependence of isoprene emission, of the isoprene emission rate. This is a reason why there is a diurnal variation in isoprene emissions, which you can impose and include in your model. Here there's another example of satellite observation of iodine oxide. So here iodine fluxes from the ocean are dependent on various factors. Yes, so it is a large part of the research focus at the moment on emissions is how natural emissions are likely to change under changed climate conditions. Right. Anthropogenic emissions, as I said, they are man-made. The production and the use of fossil fuels is a large part of this. Some of them can have a general environmental dependence, but generally, if you compare natural emissions with anthropogenic ones, you will find that anthropogenic emissions have much more a regular seasonal cycle that repeats year for year for year. Gradually over the years, you would have a change, but you would find far less of an interannual variability in the anthropogenic emissions, as you find, for instance, in biomass burning or other natural emissions. How anthropogenic emissions are likely to change in the future is a subject of much research. In the absence of having a crystal ball that tells us what's going to happen, and I don't have this and neither of you will have, so what people do is they develop storylines of likely developments of the future. These emissions will depend on changes in socioeconomic factors, and storylines that are in atmospheric science refer to them, or in climate science refer to them as scenarios that describe the likely choices in the developments that can be expected. And as there's a wide range of them, you will have also a wide range of scenarios. So population growth will be a factor, economic growth will be a factor, lifestyle choices or political choices. So current scenarios that are being used are the RCP ones, recommended concentration pathways. And so here's an example of a plot how carbon dioxide emissions might change in the future, depending on what kind of storyline you choose to follow. And it will be interesting to see then, as time progresses, how the real emissions or the emissions that have been quantified will follow these pathways. So where do you get emissions data from, or how is emissions data being made available? You can have it as annual totals per sector, but a more interesting way of representing it is having it not only the annual total, but also the geographical distribution of individual source sectors. In a gridded format, ideally, because models often are grid-based, not always, but many are, and so using gridded emission fluxes would be an advantage. So what we're seeing here, an example on the left, are anthropogenic CO2 fluxes from EDGAR with a geographical distribution. You can see that the warm colors are there in regions of high population density and associated high fossil fuel usage. on the right here, we see emissions inventory, gridded information fluxes from the aviation sector. So this has, in addition to the longitude and latitude distribution, also a vertical component, because aircraft obviously fly high in the atmosphere, the vertical scale being quite exaggerated here. And the contour that was chosen for this shows actually fuel usage, which is related via conversion factor to carbon dioxide emissions. And we can see from this that most of the emissions take place in the northern hemisphere, reflecting the majority of transport pathways for this particular part of the transport sector. So gridded distributions of the data is a common way of providing this. Either 2D or 3D by emissions type, and emissions fluxes are then provided as monthly or more frequent or annually sometimes mass fluxes in kilogram per emitted species, either per grid cell or per surface area per second. And where can we get, so let me see, that's all. So where can we get this data from? There are various websites where you can download emissions data. One example that I've used in the past, and which I think is a very good website, is the Gaia database. Hosted here at this web portal. You can register for free. You can, after entering your email address, you have access to a wide range of emission inventories, to the data from this. So some of them go many years back, some are very, very recent. This is being kept up to date. And the data is available in a format that is very useful. It is gridded netcdf or ASCII data that you can download. You can choose specific time periods that you wish. You can restrict your regions. You can get global data from the whole globe, or you can restrict yourself to specific regions. You can look at statistics of the data, like profiles, and you can also generate maps of the emission fluxes, so you can compare with what the data should look like, or what the providers think it should look like, versus what you get once you've downloaded and processed it. So there's some error checking facility there as well. This is very good, and I think part of the reason of this is that people who provide this data are linked to atmospheric modeling itself. I have to say, based on my own experience, unfortunately, this isn't always the case. So I have made use in the past of an aircraft emissions inventory that has been put together with a lot of effort by an EU project with experts from all over the world working in air traffic management, air transportation, aeronautical engineering, engine technology, architects devising runways and airport configurations, and with a lot of effort the data was provided, but it was given to me in Microsoft Access format, which is not something I find very useful. I live in a Linux Unix world. When I asked them to please can you give that to me in a gridded form, and that was very difficult and took very long. And once I had it, first thing I did, I generated a zonal mean plot of the emissions and showed that to them and said, look, is that what you expect from your data? Is that right? To which I got the answer, wow, we've never looked at our data in that way. This is really exciting. Can we use this plot? I have to admit, I felt quite crestfallen after that, and I thought, well, but this can happen when the community that makes the emissions data doesn't talk to the user community. But many of these emission inventories that are available here, they are specifically designed for atmospheric modeling. And so this is a great advantage to have the data in netcdf format in a gridded form. Okay, so for the remainder of the talk, I will look at emissions, how they're implemented in models, and particularly in UKCA. And I recently have compiled an entire suite of time-varying emissions for UKCA to be used in transient model runs. And I must say, I was astonished how many decisions have to be made and how many possible ways there are of generating emissions. And I'd like to share this with you and give you an indication of the type of emission, type of decisions that you will have to they will have to make if you plan to generate or generate emission data sets for the model. So the first choice that you need to make is, well, what chemistry scheme do I use in order to address the question, my research question? Many models, including UKCA, can be used with a range of chemistry schemes, and so this will determine what kind of compounds, chemical reactants you'll need to emit. If your interest is in simulating the change in global burdens of greenhouse gases between present day and 2100, for instance, you will look to emit different compounds than if you're interested in regional air quality with a future climate background. Then you will have to include different compounds. Your chemistry scheme will provide you with a set of tracers that are available, or chemical compounds, species that are available in the model. But sometimes, in order to represent the full reactivity of the atmosphere, you will want to include more species in your emissions than you actually have in the model. So this is typically true for VOCs, for volatile organic compounds, and in this case you'll need to lump emissions from various species that you actually don't have in your model into species that are there. These are decisions you will need to make. Another question is whether you want to have your emissions generated online during the model run, or whether you want to read them in from an external ancillary file. Sometimes there is a choice to be made. So UKCA, for instance, can calculate various natural emissions online, in the sense that the environmental conditions that determine the emissions flux can be provided by the model, and hence the model has the ability to calculate the emissions. Sometimes you might choose not to do this. You want to prescribe them, and so there's a choice you need to make. Another issue is that emissions are often provided on a relatively fine grid scale. Global inventories currently come at 0.5 degree in longitude and latitude, and some sectors are provided possibly at even higher resolution, 0.1 degrees, which is much finer than the model grid that you may choose to use. So if you add these emissions directly into your grid box, they get instantly diluted homogeneously over the extent of the grid box, and it can result in a change to the chemical scheme. You need to think about whether this possibly causes a problem in the research questions you wish to address. We'll look at this in a second. There are ways around this, but they might be computationally expensive. Another question you need to think about is the temporal resolution. So emissions on a global scale are typically provided either annually or in monthly fluxes, and your model has the ability to interpolate between these fluxes, either by putting a spline interpolation through this or linearly interpolating between the monthly fluxes. Or sometimes some models don't do this. They just change at the end of the month the flux rate without doing anything about it. Is this sufficient? Or does your research question require that you look at specifically higher frequency updates of the emissions, diurnal or weekday cycles? And as a last point that I'm listing here is, where do you put your emissions in? We think of emissions typically to be released at the surface, so you have a 2D field that is being, the flux goes into the bottom of the boundary layer of your model, and the model then transports these emissions, these compounds around. Is this sufficient? It's obvious for some source sectors, like aircraft emissions or lightning emissions, that they have a three-dimensional distribution. But you might want to think about whether other emissions also should be placed over an altitude range. An example here would be emissions from biomass burning, which typically are associated with convective processes from the heat of the fires that happen on very small scale. You should think, is your model capable of representing this accurately? Perhaps not. Then in this case, you may want to choose to spread out the emissions flux over a couple of levels, vertical levels from the surface upwards. How high you want to go, there is no magic answer to that. You have to test out what gives you good results. Another example would be emissions from explosive volcanic eruptions, which can be transported quite high up into the stratosphere. So you don't want to put these at the bottom of your boundary layer in the model. Coming back to this point that I made earlier about subgrid scale processes, because this is an issue for which global atmospheric modelers are often criticized, and there's really no magic solution. I'd just like to show you some examples of how people have tried to address this. But if you have good ideas, don't hold back. Let the people know and publish your papers. So I had to choose an example. So I've worked a lot in the past with transport sector. So this is my thing. So let's have a look at a container ship that might travel across the Atlantic through a quite clean, unpolluted marine boundary layer, and from the smokestack come emissions of carbon dioxide and water vapor, obviously. But for us, from a chemical point of view, more interesting sulfur compounds, oxides of nitrogen, and black carbon. Now, these emissions, or the plume that is released by a ship, is relatively narrowly confined. This is shown here in a graph in a paper by Peter Hussar, where they've shown data from the DLR Falcon aircraft flying over the English Channel, taking NO measurements from ship tracks. And so as they've flown along, you see these spikes every time the plane has flown through a plume from a ship, taking high readings. Obviously, this is a time scale and not a distance, but I hope you take my word for the fact that these plumes are quite narrowly confined. So what happens now if you put such a plume into a large model grid box? In order to illustrate this, I've stolen a figure generated by Daniel Carriol. They wanted to show obviously a totally different point with this figure. I'm just abusing it for my own purposes, so sorry, Daniel. This may now be, the x-axis here may illustrate the extent of my grid box. And the ship is now traveling through my grid box, and there is a plume of NOx. Here, this may show now the concentrations of my pollutant, here NOx, near the plume. As time passes, this plume would spread out eventually until you have a very flat distribution of your emitted compound throughout the grid box. Now here, where I have black shading, I say I may be in a chemical regime where I titrate NOx, where I reduce where I titrate ozone, where I reduce my ozone concentration through reaction with NO. So I'm actually losing ozone here. Whereas below this bar, I'm in a chemical regime where I'm photochemically producing ozone. And as time goes by, this shallows off here and spreads out. And if I were to put this emission flux directly into my grid box, I'm having only ozone production, but no ozone loss. So is this realistic? One way around is for people to address this problem is by including a preprocessor or a submodel that represents parametrically a large part of the plume processes that are relevant for this chemistry. So by adding an additional model that simulates the fact that your emissions are actually have a spatially heterogeneity, they are different, and their plume processes take place until actually the time has passed for the emissions to spread out in the model and correct your emission fluxes for the parent global grid box. This has been done by people, for instance here by Peter Hussar in this paper. So what we're looking at is shipping NOx changes due to including a plume model for various seasons. Here as absolute values, you probably can't read this. I can't even read this myself. So there are reductions of NOx, and you have due to the plume processes. And I wish that would come out a little bit better. However, there are some double-figure percentages in the marine boundary layer, even though the absolute emission values might be small, but you are here in a clean environment. And small changes in NOx perhaps have a chemical impact. I cannot tell from this figure, but it's something you might want to consider. Another example comes from a different part of the transport sectors, from aviation. Here, is visually even more obvious. When an aircraft flies through your grid box, often they leave in their wake these line-shaped clouds, these contrails made of ice crystals, and you can see visually how over time they start spreading out and getting dilute over time. Of course, here we are not interested in the ice. Here we are interested in the chemical compounds from the engine emissions, oxides of nitrogen. So this is a study by Ernst Mayr at KNMI in 2001, a few years back, where he included a plume processing model for aviation emissions to evaluate the magnitude of the impact when you are interested in the global ozone burden change from a specific sector. So what we're seeing here is the change in NOx at 250 hectopascal, roughly the cruise altitude of aircraft, where most of the emissions are released, in parts per trillion due to aircraft. So we can see that global air traffic here in the North Atlantic Flight Corridor enhances NOx by up to 90 parts per trillion. And here, this graph shows the relative difference between including a plume processing model and here without the plume processing model. So here, I need to stand back and squint a little bit. I hope in the printout this is visible. It's certainly visible in the PDF that will be put on the website. So you can see here is about 20 parts per trillion, so about 25% change in NOx. So what does that mean for ozone levels? The amount of ozone that is produced by aircraft NOx is relatively modest. We're talking about a couple of parts per billion here in this model, about 2 parts per billion, 1.8 up to 2 parts per billion, and you have a change of 0.1 parts per billion in ozone. So you see, if you're interested in the global impact here, this is a relatively small fraction of to a very small change of a radiatively active compound, a greenhouse gas. You want to consider whether it is worth implementing a plume processing model that will cost you computationally time and effort to include. Are the improvements or the changes that you see actually worthwhile the effort? I'm trying not to make an argument whether you should be doing this or you should not be doing this. What I'm trying to say is you should think about it. Most people don't include plume processing. Usually emissions are just being plonked into the model grid box and diluted. This is the most common practice. However, if you're interested in specific small-scale features or if you're not looking at global burdens, you should consider whether you can improve this, and you're making a mistake. The other point that I said was the temporal resolution of the emissions data. Sometimes some studies, for some studies, monthly mean emission fluxes might not be good enough. If you're interested in looking at local air quality, for instance, even all over the world regionally, what you see here are emission fluxes for it doesn't matter which compound it is, carbon monoxide or NOx, from non-traffic in red. However, if you're looking at the emission fluxes from other SNAP sectors that represent traffic, here you have a morning rush hour peak and an afternoon or evening rush hour peak with lower values in the middle. So we have here the time of day over the day. If this is the object of your study, you may want to make sure that your model have a diurnal variation. Your model considers a diurnal variation of the emission fluxes. Right. So as to UKCA, in this slide and the next slide, you see a listing of all the emissions that UKCA knows as a standard off the shelf. You can add more if you wish, but this is what the model comes with. Here on the right, we see a range of chemistry schemes the model knows as a standard and can work with. As Luke said, you will be working with the stratosphere-troposphere chemistry scheme, so the full vertical extent of the chemistry for the tutorials. And with the strat-trop chemistry scheme, the model knows 23 different emission files. Here are the gas phase emissions. And as I said, if you look at use different chemistry schemes, like here the regional air quality chemistry, you may want to consider, or you need to consider emissions from other compounds as well. Here on this page, you see emissions that are relevant for aerosol chemistry, and also if you want to use the GLOMAP mode model, if you include this in UKCA. And here's a listing of the online emissions UKCA is capable of producing. So wetland emissions of methane, lightning NOx, because lightning is tied to vertical to convection in the model, so the model will decide where geographically and to what extent lightning will take place, and will produce NOx emissions online, sea salt emissions, and organic carbon from marine sources here are also included. These tables come from a documentation paper. For the entire you get, for almost every component, or actually every component, I imagine, you get a documentation paper that you can download in its latest version from this website. The documentation paper 84 is for UKCA, and chapter 10 deals with the emissions. It's an invaluable source of information. If you start working with a model, many of you may have working experience already with a model and know these documentation papers, but if you don't, they are an invaluable source of information, and I would start with that first. And when you don't find your answers there, then contact people who hopefully can help you. Right. So emissions in UKCA. When you speak to people who have been working with UKCA for a while, they will always talk to you about, well, these are the new emissions or the old emissions. I'm very much against this kind of naming convention of new emissions scheme or the old emissions scheme. As we have seen with the new dynamics, eventually everything that is new will be replaced by something that is even newer. And this is also true for the new emissions. In version 10.9 that you're using, the new emissions are the standard. There are no new emissions. What is meant is that emissions are provided in NetCDF format. I imagine that most of you have already worked with NetCDF data files because they are quite common in the atmospheric science. They're binary data format that is self-describing. The data files have metadata information that give you information about the data that is in there and about its structure. Previously, the UKCA model had its own bespoke binary data format known as the ancillary format, which is no longer used for the emissions. NetCDF introduces a lot of flexibility because many applications can read NetCDF files right away and process them. You can visualize the contents of a file, but also you can now include multiple files or multiple emission variables for various sectors for a specific species in a file. So if you want to look at the raw emission data from the file, this has become much more simple and flexible. The metadata attributes in the NetCDF files help to avoid inconsistencies because UKCA is capable of reading those and cross-checking to find out whether the data that it reads in actually matches with what it expects, particularly, for instance, with units. Are the units kilograms per meter squared per second? If they are not, then the model will complain to you and give an error and says, no, that's what I'm expecting. Are isoprene emissions expressed as emissions of carbon or emissions of isoprene? You get a total different mass flux. So by checking with the emissions, the model can find out and apply corrections if necessary. So this is a fairly smart thing to do. NetCDF files are written in a certain standard, or should come in a certain standard. What is used in atmospheric science a lot is CF, whatever it stands for, I do not know, climate and forecasting or something like this. Yeah. However, the NetCDF files strive to get towards the standard. They boldly claim, yes, this is CF compliant, but they not always are. But we're getting there. The old ancillary files are only used for two remaining files from oceanic sources, DMS and chlorophyll. And the reason for that is that they are actually not emission files, but they are files that contain seawater concentrations of these from which the model then calculates emission fluxes directly. And these concentrations could also be provided by an external ocean biogeochemistry model, for instance, if you run UKCA as part of an Earth system model. So here, there is a list of the, a listing of the attributes that can be used for emissions that the model knows. Some of them are mandatory, some of them are not, some of them are optional, and we're going to have a look at a few of these now. So this is all taken from the 84 UNDP paper. Okay, so in a NetCDF file, the variable, the emissions flux variable, will have its own attributes. However, the whole file can also have global attributes. You can include as many attributes as you want when you generate emission files. However, there are two that the model needs at present, which is the update frequency in hours, one of them an update type. So the update frequency in hours tells the model how often it needs to update the emission fluxes. So if your data provides monthly mean fluxes, a function will smooth out these fluxes over the course of the year in a way that the entire mass over the year is preserved. However, this requires an adjusting of the emitted fluxes ever so often, and here this is set to 5 days, 120 hours. You can change this. However, the way it is set up at the moment, this cannot be changed in the model. This needs to be changed in the emissions file. Perhaps in future versions, this is a switch that can move into the model. I had discussions with this with Alistair Seller, and he said, yeah, it would be much better to have it in the model rather than in the file. The other point here is the update type, which tells the model what kind of data I actually have in my emissions file. Perhaps there is just a single time step that is perpetually applied, which might be appropriate for some emissions. The opposite of this would be a time series. So you have an origin given in your NetCDF attributes, a time origin and a time variable. And if your model run starts on the 1st of September 1975, the model will look in your emissions files for the exact data point that corresponds to the 1st of September 1975 and start reading the emissions from there. In this case, your emissions file, of course, needs to be needs to extend over the whole duration of your planned model experiment. And the last option here, periodic time series, would be if you have a 12 monthly fluxes, one seasonal cycle, one annual cycle in there, which is then perpetually applied. So you have exactly 12 time steps. If you set this to 2, and you have many actually a very long time series that's happened to me recently, is the model will only read the first 12 time steps and repeat these forever. And you think you're varying your emissions, but it doesn't. So be careful with what you said. In old emission files, you also find the attribute emission type, which does exactly the same thing as this. However, this is deprecated and is no longer used. Now, moving from the global attributes to the NetCDF attributes for the actual variable that describes the emissions flux, you can put a name field. However, that is not read by the model. That is not used. What you need, definitely, is tracer name. This has to be equal, so it's an attribute called tracer name, and that has to be equal with the name of the species in your model. Through this attribute, the model actually knows in which tracer these emissions have to be put. And if you put a tracer name that you don't have, so if you say, please put this into isobutane in the model, and you don't have isobutane in the model, then the model will crash and will tell you, no, sorry, can't do. A standard name, that is something that comes from the CF compliance. Standard names have been developed in order to allow, to facilitate easier exchange of NetCDF files. So if you provide an emissions file to someone else, for instance, if there's a model intercomparison project and every participating modeling group is supposed to send their data in, then if they all match with provide CF compliant NetCDF files, then the standard name for the same kind of data should be the same. So that avoids ambiguity and misunderstandings. However, these standard names are quite a mouthful. Unfortunately, they're not that straightforward. You see, for instance, for an emission of nitric oxide, it would be tendency of atmosphere mass content of nitrogen monoxide due to emission. Yes, with underscores for the standard name attribute. A whole listing of the standard names that currently exist can be found here on this website, and you will find that not all emissions that we have in the model will have a matching standard name yet. These tables are being updated and more is being added to it. However, if there is no standard name available, you cannot just make one up similar to this. The model will complain. It will find out, no, the standard name does actually not exist. Then in this case, you need to use the long name attribute, where you can write in whatever you like. It would be prudent to keep it similar to this to avoid misunderstandings. But you can also say these are surface emissions of nitric oxide. That's no problem at all. Units need to be given. Standard is kilogram per meter squared per second, and you have other attributes that give you hourly scaling, for instance, what is used for isoprene emissions, daily scaling, so for weekdays, or vertical scaling for smoothing out your emissions over a vertical emissions flux over a vertical range. Yes, so as I said, the model expects emission in units of kilograms per meter squared per second. Sometimes there's the possibility to express an emissions flux in various ways. So you could provide NOx as NO2 or as nitric oxide, or just as emissions of nitrogen. In the same way, isoprene could be, or other VOCs could be expressed as mass flux of having the molecular weight of the species, or as a carbon flux. And the model can then correct for this. And in order to do this, you must have both, either in the standard name, if it exists, and if not, then you must do this in the long name, the following wording: expressed as, and then nitrogen, carbon, or not. So this is what the model code looks for in these attributes. If it says in there expressed as nitrogen or expressed as carbon, then a correction factor for the molecular weight of the species will be applied. This is, however, not possible for absolutely any emitted species, so you need to check in these routines whether for the emissions that for which you want to use this, this has been implemented yet. Otherwise, you need to add to the code. Right. So here's an example of a header of an emissions file looks like. So this one has 732 monthly time steps. This is from 1st of January 1960 to the end of 2020. This is the time range that I was interested in. What we're looking at is SO2 emissions, and here SO2 emissions at high level that are not put in at the surface, but slightly above the surface. So here there is the standard name, tendency of atmosphere mass content of sulfur dioxide due to emission. I've used a different long name. Units given here, and this is here the attribute of vertical scaling, high level. When you set this, then the model knows, okay, this doesn't go in at the surface, but might spread over a vertical range. And here the highest and lowest level happen to be the same, so it's being put in at a level, I think this is roughly a kilometer above the surface. And that's where it's being put in. So these are SO2 emissions from specific sectors that are being lifted up particularly. This is not the entire SO2 that goes into the model. And here global attributes, as I said, you can add to it as much as you want, but you must have update type and update frequency. If you want to be CF compliant, then you need to add a few others as well, like institution is required, source is required, a title is required, a reference should be included, so you can add to whatever you want. The reason why we add these is to help people who might get hold of your emissions file and want to know what's actually in there. And this is the whole point of documenting the emissions process, because I've spent a lot of time running models in the past that came with emissions, And when I asked, well, what data is in there? What goes into the model? Quite often I got a shrug and said, well, I was referred to some obscure paper that was published somewhere in the grey literature where about a quarter of the emissions were described. So nobody knew what was in there. And I feel very much if somebody changes something in the emissions, as the emissions are at the beginning of the whole process, it is important to include this. So in order to do this and to document this, I've gone through the trouble of writing a quite lengthy wiki page that describes how I put together emissions. And if Luke permits me a few minutes still, or just the two, you have a printout, yes. So therein I've described how I put together emissions, what choices I've made. It's obviously grown higgledy-piggledy, this website, so it's not very elegant, and I've developed it as I went along. Looking back, I've thought of many ways how this could be improved. What I found is there are many ways how you can make emissions, there are many wrong ways how you can make emissions, but a few points I want to point out here. There was a requirement to have emissions from various sources. Not everything comes from the same database. You need emissions, and you need to make this clear where your data comes from. You need to find out which ones do you want to lump together, what makes sense, as I mentioned before, and where do you stop? You could lump forever higher order hydrocarbons into your alkane emissions. The unified model is one of the few global climate models that are still capable of running with 360-day calendar settings. There's a move towards Gregorian calendar, so the real 365-day, 360-day calendar, which is used if you run the model in nudged mode, when you relax the dynamics towards meteorological analyses. However, if you run in a free mode, in a climate mode, where the model calculates its own dynamics and temperatures and whatever it needs, then it's typically that you have 30-day long months, and the model runs with a 360-day calendar. This has implications for your emissions. If you're interested in keeping the annual total of your emissions constant, then you need to apply a scaling factor. You need to provide two different sets of emissions, because the other calendar is 5 days longer. And if you have a monthly emission flux, then you have 5 days more emissions, so the annual total might be slightly larger. The difference is small, however, it depends what you're interested in. The current reading is, or the current standard is, that Gregorian emission fluxes are used for either 360-day calendar and 365-day calendar. The thinking of which is this is relevant for relatively short-lived compounds, because the emission flux needs to match with the loss processes, like deposition or chemical loss processes. And by changing the calendar, changing the emission flux, you create an imbalance that has a stronger effect or more important impact on the chemistry than the fact that you actually increase your annual total emissions slightly by a few percent. This is for the short-lived compounds of relevance. Long-lived ones like N2O, carbon dioxide, or methane perhaps there you want to stick to your annual totals and want to apply some scaling. But for those chemical compounds that we're looking at, actually it is the current method of working with it. You stick to the Gregorian fluxes with which the data comes. You will generate your own emissions files as part of the tutorials, and for that you need to apply a mass-conserving regridding mechanism, so that data doesn't come on the model grid, on the N96 grid, or whatever version you use for your tutorials, perhaps a lower resolution. You need to regrid your emissions, and there you can't just do linear interpolation in space. That would not conserve the emitted mass, so you need a specific algorithm. For all this is code available, and if you permit me to click quickly on this, can I just click on this? Yes, I can. So if I go here, so this is this website. No, I can't see it. How?
Go on to a different screen.
Ah. How?
They've got a printout of it.
They have a printout. Okay, so if you go through this, if you look at the printout, I see it now on my screen, but there comes, first of all, comes a very large table which I privately refer to as the mother of all tables, which has taken me a long time, but it shows you exactly what species have been lumped together into what tracer and what sources the data comes from. It shows the, I think it's 23 emission files, so it will probably extend over various pages for you. There are then links to a GitHub repository where the software that I developed for processing the emissions from the raw data to the final NetCDF format the model reads can be downloaded. This is a mix of both IDL and Python software. With hindsight, of course, it would have been better to improve this, and I'm not recommending that you use this, but I can say if you wish, you can look at this and use it if you think it's good for you, and modify it and work on this. You can use this as a template if you wish to change your own emissions. For the part of the tutorials, you will be given code that does this. So you don't need to code regridding emission interpolation stuff yourself. You have this. And right. So coming back to the other bit. So now I'm lost. Anyway, the last slide that follows this would have been my summary page, which is, I have to admit, not quite, which reads a bit lame. I think everything that was important that had to be said has been said. I think what I've done so far, I've shown why emissions are important because of them being standing at the initial outset of the chemical processes. It is important that you quantify your fluxes correctly, but there are a lot of choices to be made when you put emissions in, and we've discussed various of these points that you need to think about. If you want to work with emissions and you have questions, you are welcome to contact me, email me, find me. I'm not the expert who knows all the answers to emissions, but I've done it. I've put together emissions for UKCA. I can tell you what choices I made and why I made them. There is a paper in preparation for geoscientific model development on the axis emissions, and when that is out, many of these choices will also be described there. For now, I thank you for your attention. I hope you enjoy this course, and if I have time, then I'll drop by when you do tomorrow. We will work on the emissions, and if there are any questions in the practicals, then do come and ask me. Thank you very much for listening.